Hi, the lecture today is about calculating the area between the curves. Well, whatever area we try to calculate is by definition between several curves. The intention of this section in the text is about looking at regions that are a bit more general than the pictures we have seen so far. What is it that we have studied? We have studied area of regions that look like this. You have typically a curve given as y equal to f of x. Then you are given some starting point A and some ending point B, and down here is your other curve, which is x-axis, which has equation y equal to 0. You are trying to find out the area limited by these curves. It just so happens that 3 of the curves are actually straight lines. So what was the area? Area turned out to be integral from a to b of f of x dx. How did we calculate this thing? Suppose you know the antiderivative of f. So suppose you know about the function capital F, whose derivative is a little f. So f is antiderivative of f. Then that area simply turns out to be f, capital F, calculated at b minus same thing calculated at a. That is value of this definite integral. Our objective today is to look at pictures that are more general, perhaps more complicated than this one. We can go in one of many areas, and the first thing that we are going to look at, item 1 for us. So what if the bottom of the picture wasn't as simple as just an x-axis? What if I had a region that top of it was given to me by a function y equal to f of x, and the bottom of it, instead of being the x-axis, was some other curve, say g of x. To keep the problem manageable at this level, the left and right is still given by a straight line, vertical line. So this is A and this is B, and our objective is same as before, to find out what is this area. Now we are going to have a long list of various cases that come up here, and then later on in sections on calculating volume, and then calculus 2 and 3. My general advice about all of these cases is that you try to learn the principle involved as opposed to trying to memorize the formulas. There will be a very long list of very similar sounding formulas, and the way to get around it is by understanding what is involved in each of these, which is essentially the principle that is involved is how do you cut up this region to manageable areas, and how do you construct your integral. So before we get down to the formulas and such, let me just make a list of different kind of regions we might be interested at. There's a type 2 regions that we are interested in. Sometimes these parallel lines aren't vertical, they could be horizontal, and the picture would be just lying essentially on the side, extending in a horizontal direction. The picture could look something like this. You might have some sort of a curve like this, and beginning and end of it, of the region, might be drawn in this fashion, and you're still interested in calculating this area limited by these curves. This is very similar to what we have seen here. It's just that you have to get used to essentially renaming of your variables. So in this case, you have a function that is given by x as some function of y. Okay, for any value of y here, you specify what the x is supposed to be, as opposed to the other way around. Once you get the hang of this, we might as well go ahead and take a look at some cases where picture looks like this. You might have x as a function of y, and another one here. Let me just keep my terminology similar in all these cases. Change this thing back to, and this one x as some other function of y. And traditionally we use a and b for the x-axis and c and d for the y-axis here. It doesn't matter what you call them. Again, the problem would be to find out this type of area. And later on we are going to look at different shapes that could be considered perhaps in two different ways, and we'll have approaches for them as well. Let's go ahead and work on the first category. How do we approach this problem? We think about it this way. Say this is a picture that is essentially vertical. It's better, we are better off if we slice it in this fashion. We create our rectangles like this. What does that mean? Well, that means that we have width of the rectangle here being given as dx. This is the x-axis, and this small width here will be dx. How about the height of this? Well, the height of the rectangle is the difference between the y of this curve and the y of this curve, or it's going to be f of x minus g of x. This height is f of x minus g of x. So if I want to find the area here, all I have to do is to multiply these two, multiply dx by this difference. That's going to be the area of one of these rectangles. Then I have to add up all similar rectangles from beginning to end. Let me go ahead and do the picture again here. So we said we have f here, and say g below that one, and then we are starting from A and want to go as far as B. We create a slice that's going to be dx thick, or delta x thick if you wish. This slice is going to have a height here. So I'm looking at this triangle, the rectangle. The height of this is f minus g, and so the area I want to calculate is going to be f of x minus g of x, which is going to represent the height, and that's multiplied by dx, which is the width. And then I have to do my integration from a to b, so I'll just calculate the integral from a to b of this, and that whole thing is just going to be the area. Now remember that you could write this same formula in another way, which is to write it as f of x dx from a to b minus g of x dx, that one also from a to b. What do each of them represent? Well, the first one is the area of the region under F, that is, if I was calculating this area, that would have been this expression. How about the second integral, integral from a to b of g of x dx? That is going to be this other area underneath g. So what are we doing? We are calculating area under f, and calculating area under g, and subtracting them afterward. That is the meaning of this right hand side here. The meaning here is that we are subtracting f and g to find the height between them, multiplying by dx to get the area, and then integrating from a to b, and that's going to give us the same thing that we are obtaining on the right hand side. Let's go ahead and practice this problem. Here's an example. Okay, here I have an example. Find area under y is equal to 2 plus x squared over 2 and over, or let me change my wording, and above y is equal to x squared over interval from -1 to 1. Now in this problem we are giving a curve for the top portion, another curve for the bottom portion, and we are specifying the left and the right. Everything is given. We don't really need the picture, but it helps to have something in front of us when we are doing one of these problems. 2 plus x squared over 2, suppose this is 1 and that is 2, and we have a kind of white parabola, and the other one is x squared and the problem itself tells us that we are going from -1 to 1. So I might as well specify what this one was. This was the top portion, y is equal to 2 plus x squared over 2. This was the bottom portion, y is equal to x squared. The area we are interested in will be then this. What is that area? Well, we learned top minus the bottom, so I write 2 plus x squared over 2 minus the bottom, which is just x squared, and then I'm going from -1 to 1. This is the integrand, and here's my differential dx representing the thickness of the panels we are constructing. Well, all that is left to do is just to calculate the integral. That's right, -1 to 1, this is 2 plus x squared minus x squared, I get minus x squared over 2 dx. Integrating this thing, I get 2x minus x cubed over 6. That has to be evaluated at 1 and -1. Next stage, we go ahead and substitute. I put a 1 in this, I get 2 minus 1, 6. Then I put -1 in it, -1 plugged into 2x, I get -2 plugged into this one. Remember, minus cube becomes still minus, with another minus makes a plus. So 2 minus -2 is going to be 4, -1 minus another, excuse me, minus 1 6, another minus 1 6 makes 2 6, or 1/3, and it looks like that all boils down to 11/3. Okay, so that was straightforward. Let's just remind ourselves what were the ingredients here. This one was equation for the top, this one was for the bottom, this one was for the left, and this one was for the right. Okay, in essentially any kind of integral, you need to have these 4 ingredients. You need to have a mental picture of what's going on, have the 4 ingredients for yourself, and decide how you want to cut up the region and go along with your problem. Now remember, we said we want to look at a variety of type of region. This one was a region that is essentially vertical, meaning we have 2 lines which are the left and right of the region. They are vertical, and it makes sense to start with cutting this region up in this fashion first. You have many other choices, but perhaps this is one thing you should consider first. What if you had a picture lying on the side like this, when x is given as a function of y? This is the simple case, and this would be similar to what we looked at problem number 1. Well, it makes sense to try to cut this up horizontally. Let's create your slices this way. You could try cutting it up in a vertical fashion. That's a possible approach, and perhaps sometimes it might be actually better. But our first approach should be going with the general flow of the shape and general direction that we have. So if we decide to do it this way, the role of x and y are going to be exchanged. Now my thickness here is going to be labeled as dy. dy is going to be how wide this rectangle is going to be, and the length of it is going to be x calculated at the right minus the x calculated at the left. Other than that, there isn't any difference between these 2 cases. It's just getting used to looking at picture sideways, and aside from that, the concept is exactly the same. Just to see that these are actually really the same pictures, let me go ahead and rephrase the problem we just did. Example 2, find area to the left of x is equal to 2 plus y squared over 2, and to right of x is equal to y squared between y is equal to say minus 1 and y equals 1. Well, what is meant here okay, here's our x-axis, here's our y-axis. X equal to y squared, that's going to be a parabola that opens in the x direction. You give value to the y. For example, when y is 1, x is 1. When y is 2, x is equal to 4. When y is minus 1, x is 1. When y is minus 2, x is 4, and so on. So here is the picture of the this is x is equal to y squared. How about x is equal to 2 plus y squared over 2? Well, that's going to be perhaps here's 1, 2. When y is 0, x is 2, when y is 1 or minus 1, this is going to be 2.5. So rather wider parabola when y is equal to 2. This makes 4. So this is a picture of x is equal to 2 plus y squared over 2. So we want the area that is to the left of this one. This is a picture. We want to be to the left of this. We want to be to the right of x equal to y squared, and we want to be between y equal to 1 and y is equal to minus 1. So eventually, where do we want to be? This is the region we are interested in. Okay, we said first thing we try is to slice this up in this fashion. Okay, we calculate the area of each of these rectangles and then add them up. Well, how thick is this? The thickness of it is dy, differential of the axis that describes the direction perpendicular to the direction we are cutting. We are slicing it this way, and the differential is going to be perpendicular to the direction of a slice. That direction is y, so our thickness is going to be dy. Well, how long is this? Well, you find the x here, and find the x here, and subtract the two x's. You find out how long this is going to be. X on the right is given by this formula. X on the left is given by this formula. You subtract these two. So I write the right one first. That is 2 plus y squared over 2. This is right. This is left. The result of this subtraction is how long the rectangle is. That length times the width is the area of that little slice. Then I have to add up all the pieces. How do I add up? I start from the lowest value of the variable from -1, and I go to the highest value. So in this version, this became the right, this is the left, this one is the top, and this one is the bottom. Y indicates that our slices are perpendicular to the y-axis. Slices are perpendicular to the y-axis. Well, what is this? This is exactly the same integral we saw over here. Just that instead of x, we wrote y. That's why they call them dummy variable. It doesn't matter what letter you got here, so long as the integrands are the same for the same values of the variable, you're dealing with the same integral. So if you go ahead and do this, you better get the same answer that we got here, and that answer was 11/3. So I just trust that this answer will turn out to be 11/3. Okay, so we learned a little bit about turning our heads to the side and looking at the pictures, perhaps in ways that might look new. Let's go to some other challenges in these type of problems. So let me just make a heading here, other challenges. Well, one challenge would be that some of these ingredients have to be determined by you. Most common, you have to figure out the limits of the integral yourself. as opposed to problem which is feeding that item to you. Another challenge is to figure out who is on the left or who's on the right, or who's on the top and who's on the bottom. In these problems, the problem itself tells you where each of these pictures are situated. Since it tells you, you really don't need the picture. Here is your the ingredients. You know this has to be on the farmost to the right, and this one is the item on the left, and you subtract them. Or in this problem, maybe the language clearer here. This is the top, and this one is the bottom. This is the left, and that's the right. So you have the 4 ingredients for yourself, and you can do the problem without drawing a picture or paying attention to any details. But sometimes these are left to you, and the problem becomes a bit more challenging. Here is an example. Find the area between say y is equal to x squared and y is equal to 5x plus 6. We are not told who's top, who's the bottom, where's the left and where's the right. So we might as well go ahead, get a picture of this situation to be assured of our answer. So y equal to x squared, well, that's just a simple function. Go ahead, draw a nice parabola here. Suppose this is y equal to x squared. Y equal to 5x plus 6. 5x plus 6 curve with rather, I have to change my scale here to be able to fit my picture. Let's just for the moment let's assume that this is 5x plus 6. It has a positive slope and it has a positive y-intercept, so it has to start somewhere high up here and then slope up quickly and go up. Well, we are told find the area between these. Let me draw another picture, perhaps smaller scale. Here is a parabola and here is a line. What do you mean by the area between these two? Well, we have some area here if you wish. We have another area here. We have still another area here. Here is another region which is limited by these curves, but I'm sure all of you guessed by now that the area that is meant is this limited region or the bounded region, sometimes an area bounded by these two curves. That's what we want. Why that one in particular here? Well, all these other ones, the area is infinite, and the measure of area is infinite and is also unbounded. So here we have to kind of read between the lines and understand that that is what the book wants or what the problem wants. Another issue is, well, who's on the top or who's on the bottom? From this picture it becomes clear that 5x plus 6 is on the top in this region and y equal to x squared is on the bottom. Next question, who is on the left, who's on the right? That is, our area starts from here and ends at here. So where are these two locations? Those vertical walls have turned into just a single point at these two endpoints. How do we find them? Well, these are points of intersection of these two curves. So the way you find it is to say that if the y's, if they're meeting each other, y's have to be the same, and so x squared becomes equal to 5x plus 6. If the two curves meet, it means the value of the y's are the same, and therefore you can equate the two sides and go ahead and solve this. Well, this turns out to be a simple quadratic equation. You factor it and you get x minus 6, I guess, times x plus 1 equal to 0, and you get x is equal to 6 and x is equal to -1. So this point is supposed to be 6, this point is supposed to be -1. My picture isn't drawn well enough, so scales is not quite right. Sorry for that, but we are going to move on. The area we are after is this area. It's better to cut this up in a vertical fashion, and we are going to go ahead and write the area is equal to the top. We write the top first, 5x plus 6 minus the bottom. This whole thing is going to be like the height of one of these rectangles. If you want to cut this up in one rectangle, that's how tall that is. The width of it is going to be dx. Starting point is -1, ending point is 6, and now we are done with 80% of the problem. Now we progress from here. I have integral from -1 to 6 of 5x plus 6 minus x squared. There wasn't much simplification on this step. Integral of that is 5x squared over 2 plus 6x minus x cubed over 3, in which I have to plug in the two numbers -6 and -1 and 6. So 5 times 6 squared over 2 plus 6 times 6 minus 6 cubed over 3. That's what I get when I plug 6 here. Then minus, always keep these parentheses for safety's sake, -1 apply here, 5 times -1 squared over 2, 6 times -1 minus -1 cubed over 3. Okay, 36 divided by 2 is 18, times 5 is 90. That is 36. 6 cubed is 216, divided by 3, 72. Then we'll have minus, this is going to be 5 halves. Minus minus makes plus. Plus 6, yes. And then here I have 1, 2, and 3 negatives. That makes minus 1/3, I believe. Okay, perhaps a good way to handle these kind of problems is to total whole parts first, and then see what you want to do with the fractional parts. So here I have 126 minus that's going to be 54 plus 6, that is 60, minus 5 halves minus 1/3, I believe. Let's see if that's correct. If you want to take common denominator now, or you want to simplify these fractions, it's a matter of style. 6 360 minus, I believe, minus 15 minus 2 makes 346, and that is 57 and 1/6. Oh, I converted decimal at the end. Okay, either of these two would do fine for us. The answer to this problem. Okay, let's do one more problem similar to this. Find area between y squared is equal to 2x plus 6 and y is equal to x minus 1. Let's try to get a picture of what's going on. You did a lot of practice on graphing. That should come in handy here to quickly guess as to what is going on. We don't need the substantial detailed graphing, but some general picture will help. Y squared is equal to 2x plus 6. What kind of a picture is that? Well, here you're essentially starting with the value of y and figuring x out of it. This is essentially a version of x equal to y squared. It's a parabola that opens to the right. This is a straight line. However you wish to think about it, that would be still just a straight line. So if you want to see the parabola here directly or convert it to a function format, you can write this as x is equal to y squared minus 6 divided by 2. If you want to write this one in same style, you write it as x is equal to y plus 1. So these are, we are looking at the pictures as x's in terms of y's. What does this first one look like? When y is 0, x turns out to be minus 3. So here's the x-intercept of this picture. Let's say 1, 2, and minus 3. When x is 0, y is plus or minus square root of 6. That is like 2 and 2.2 or something. So we have one parabola here. X is equal to y squared minus 6 divided by 2. The other one is x is equal to y plus 1. When y is 0, x is 1. And when x 0, y is minus 1. So this is a x is equal to y plus 1. We want the area limited by these two. Again, there are 1 here, 2, 3, 4, and 5 different regions. The one that is meant by the problem is the area that is limited by these two. That is the area. Well, what's a good way of slicing this thing up? You have actually a choice, but the easier way of handling the problem is to slice it up in the horizontal direction. That is, make your rectangles like this. In that case, thickness is going to be dy or delta y, and the length of this is going to be x at the right minus x at the left. Let's go ahead and do this, and I come back and explain what's going to be more complicated about this problem if you wanted to slice in a vertical direction. Okay, so slicing horizontally, we have a dy for the thickness. Now I have to find the height of it. X at the right is y plus 1. X at the left is this, y squared minus 6 over 2. So this is the length, that's the width. Now I have to integrate. Next challenge is integrate from where to where. So here's a question. Where is the start and where is the end? Just like the previous problem, if you want these to intersect each other, then the x's have to be the same. If x's are the same, these two are the same. So that gives me a equation to solve. Y squared minus 6 over 2 is equal to y plus 1. Cross multiply, y squared minus 6 is equal to 2y plus 2. Bring everything to one side. Y squared minus 2y minus 8 is equal to 0. Factoring this is y minus Is that y minus 4, I suppose, times y plus 2 equal to 0. That gives us y is equal to 4 and y is equal to minus 2. So this is minus 2 and that is 4. You could check it, for example, put minus 2 for this, get x equal to minus 1. Put the minus 2 here, comes 4 minus 6 over 2, that's also minus 1. That indicates, same answer indicates they have collided at this point. So the offshoot of all of this thing is that your integral goes from minus 2 to 4. That's what the area is supposed to be. Now we are done with 80% of this problem. We want to go and finalize it, that we have to actually calculate this. So area is integral from minus 2 to 4 of, simplifying all of that, let's write it in order, minus y squared over 2, and then I have a plus y, 1 minus 6 over 2, that's a 3, that makes a 4. So I wrote my integrand in standard form. Now I go ahead and integrate. This thing is minus y cubed over 6 plus y squared over 2 plus 4y. I have to plug minus 2 and 4 in it. Okay, so we are going to go ahead and plug these numbers. Let's see what happens. I plug 4 here, I'll get minus 64 over 6, and then it's going to be 16 over 2 plus 16, and then I plug minus 2 in it. Minus 2 cubed is minus 8, with another minus makes it 8. Next number is going to be 4 over 2, and next number is minus 8. It's a good idea to combine similar fractions first, like here 6 minus 64 minus 8 makes minus 72. Whole numbers we have 16 over 2 is 8, and 16, this is minus 2, and that is plus 8. Okay, so I kind of rearrange things in the hope of simplifying fractions. Like this minus 72 over 6 is going to be whole number here, minus 12. So again, combine similar denominators first, simplify as much as you can before taking common denominators, so that there are fewer chances of arithmetic mistakes at this level. 16 and 16, 32, minus 2 is 30, and the whole thing boils down to 18. Okay, so we have seen the problem from two angles, regions that are essentially vertical, regions that are essentially horizontal. The next challenge that comes up in some of the problems is where what you perceive to be top or bottom of the function crisscross. You might have a function that behaves like this, and another one that behaves like that, and perhaps you will have your start and ending at some location like these. So let's go ahead and call these things. Suppose I have y equal to f of x, and here I have, y is equal to g of x. The idea is to calculate the physical area between these two. That is, we are interested in this area. So what's the challenge again here? The challenge is that it's not just a single function that plays the role of the top and the other one playing the role of the bottom. They exchange their location. So here g is on the top. Here let's write, here is g, and here is f, Now f has come here and the g is down here, and then again g is on the top here. I made a mistake, it looks like. Sorry, so I have to correct myself. So this was G, and this one was F. So what's the cure in this case if you want to actually calculate the physical area bounded by these two curves? Essentially, your choice is to go ahead and cut up your integral and regions into several sections. Like come up to here. Let's call this point C. Do one round of problem from A to C, where you know F is on the top and G is on the bottom. And then do another round from, say, C to this other intersection D, where now you know G is on the top, F is on the bottom, and then exchange the roles again between D and B. F's on the top, G is on the bottom. Problems like this tend to be a bit tedious, that you have to repeat the same thing several times. But we could just go ahead and write a formula that's nice and comforting. Area between y is equal to f of x and y is equal to g of x over interval from A to B is let's see. What is the difficulty? The difficulty is that you want the height to be a positive quantity. If I use f minus g in this region, what I really need is g minus f. So how can I cure that? Very simple. Just put it in absolute value. If you write f of x minus g of x in absolute value, then the absolute value automatically corrects the sign for you. So if f minus g here is negative, but the absolute value forces it to be positive. So that's the height multiplied by the x, that's the width, and then you are supposed to integrate from A to B. Now there's a bit of cheating involved here. Is this doesn't really cure anything. In practice, when you want to solve this problem, you will be forced to go ahead and find the C and D and treat this problem into 3 separate sections anyway. Perhaps the only comfort it gives you is that you don't need to have a very precise picture. You don't really need to know who's on the top, who's on the bottom. All that you have to do is to calculate the contributions from these 3 portions, take the absolute value of them, force them to be positive, and then add them all together. That might be a bit too involved for us to get into any further than this, but the procedure is clear enough for any of you who want to actually take this up and continue to its final conclusion. Let me just say one more word before we go on. Sometimes we can give an answer for one of these problems by paying attention to the geometry instead of working a lot about calculating the integrals and such. So here is an example that might come up. Let me first ask you the following. What is the integral from, say, -5 to 5 of, say, x dx? Well, the problem is simple enough in this case that you can go ahead and find the answer. But sometimes you come across examples of these where the integration itself is perhaps not easy at all, and something about these limits and the format of the function might give you a clue as to what the answer might be. For example, here you know that the graph of x has a special symmetry. Here's a graph of x. And our beginning and end is just from -5 to 5. But in this case, when you are finding these integrals from -5 to 0, whatever you find is going to cancel out the contribution from 0 to 5 in the following sense, that if you have a rectangle here which gives you a contribution to your Riemann sum, there's another rectangle on the other side which gives exactly the negative of that contribution. They cancel each other out. Or we say the function is symmetric with respect to origin. If you change x to -x, the value also changes. So the upshot of this whole thing is that contribution from this side and the contribution from here cancel each other out, and the final answer will be 0. This problem is straightforward for you to calculate on your own and find out the answer is actually like that. Now, if the problem had been made much more complicated, like if I had written x times x to the power of 4 plus x squared plus 5 to the power of 10, say from -5 to 5. I would say the answer is again 0. I don't need to redo any work because this function, the whole thing, is having symmetry with respect to origin. If I go from right to left, the value goes from positive to negative. And since my domain of integration is also symmetric, that makes the contribution from the left and right to cancel each other out, and the net integral will be 0. So these are cases where they fall under application of symmetry. To definite integrals. There's also another symmetry you study in basic math, which is symmetry with respect to y-axis. Suppose you want to calculate the integral of dx, x squared dx from -3 to 3. Again, the problem is simple enough for you to just go ahead and do it without being concerned about the symmetry, but the idea helps later on when we are dealing with more complicated problems, especially in 3 dimensions. The region of integration is from -3 to 3. We notice this function has symmetry with respect to y-axis. Left and right are the same. So the area that you want to calculate here, the one that you want to calculate here, are identical to each other. This problem is saying add up all the areas. You might as well go ahead and calculate area of half of the picture. This one, for example, is on the right half, and double that up. What we want to emphasize here is that this is true for functions that are symmetric with respect to y-axis, or so-called even functions. When they are integrated on a symmetric domain, you can do half of the integral and just double that up. And then how do you continue? Well, the problem is simple enough for you to continue this and finalize it. For example, you write twice x cubed over 3 here, and now you have to put 0 and 3 in it. 3 cubed is 27. That makes 9 times 2 is going to be 18. Okay, you go ahead and do the problems of this section and make sure you pay attention to the possibilities that you have ahead of you. Taking a region and slicing it either horizontally or vertically, that's perhaps the main topic in this section. I hope you do several of these problems. Good luck and God bless.